Delighted to be here today at UTS with Dr. Daniel Carter, who recently was awarded one of our Neuroblastoma Australia research grants. I wanted to ask Daniel quite a few questions about his research, so I invited myself over to UTS to put some questions to him. So firstly, Daniel, thank you very much for joining me today.
Thanks for being here.
And I just wondered if you could just start off by introducing yourself as to what your research is about and why you do neuroblastoma research.
Okay, yeah, my name's Dr. Daniel Carter here at School of Biomedical Engineering at UTS. So my research is focused on neuroblastoma, of course, but yeah, in particular drug resistance and understanding how neuroblastoma evolves and changes at the single cell level.
Thank you, Daniel. And in particular, you put forward a project to us for a research grant, and obviously it was successful. Our scientific advisory board thought it was a really innovative research proposal. What do you think, in sort of simple terms, makes your project exciting and different to what else is out there?
Yeah, well, I guess it's using new technology. So one of the difficulties that we've had is trying to resource funding for brand new sort of research. So what we've got now is technology that lets us explore the genetics of individual cancer cells. So the reason this is important is because in neuroblastoma, like a lot of cancers, this variation in the individual cancer cells means that cells have a kind of mechanism by which they can evolve or adapt to acquire drug resistance. So we want to explore using a technology that not only looks at the single cell genetics but also tracks the cells in the process from before treatment to after treatment to understand what it is, what genetic features allow for these sort of small populations of cells to ultimately resist the existing therapies and then relapse as a kind of drug-resistant tumour.
So in effect, you're sort of tracking the development of cells sort of before treatment, during treatment, and then if there's a relapse, you're looking again at what's happened. Is that a simple explanation, or?
Yeah, no, that's correct. So
Yeah.
we have multiple ways of looking at
Yeah.
this. So we looked at the actual
Mm-hmm.
patient tumours
Mm-hmm.
at various treatment stages. So we've been able to compare what a neuroblastoma starts like to what it sort of ends up like. But we also have some technology which we can modify neuroblastoma cells in the lab, and then that allows us to effectively have a barcode which lets us say which is the cell that survives treatment, and then track back those unique genetic features that gave that cell the ability to survive, basically. Right. Yeah.
So it's really trying to sort of hone down and identify these critical cells that are responsible for relapse, which survive currently all possible therapy that it's being subjected to. It still survives, mutates, and then obviously causes further disease. So it's really using this new technology, absolutely trying to identify what's responsible behind these relapses. So that would be amazing. Obviously, if we can get that to happen. And just in terms of barcoding, how does that exactly work? I've got this image of a barcode. Is it literally like a barcode that you get in the supermarket?
In essence, it's basically a genetic barcode. So we can deliver this genetic material into the cells, so that they forever have this trackable genetic barcode. So when we go and undertake sequencing of the cells, we can trace it back to the cell which was basically pre-existing before treatment, and then after treatment when it became enriched or showed basically it's evolution. The cells are the survival of the fittest. They're actually being able to survive. When we may see most cells respond to chemotherapy in a patient, there's this minor population of unique cells which remain hidden and ultimately come back, as you said, for relapse. So that's what makes them drug refractory, that they don't respond to any therapy at relapse. So critically important, not just to see what a relapse tumour looks like, but where it started, because if we're going to, in order to prevent relapse, we've got to be able to see them early in treatment. So we think this has two direct outcomes or potential. So to begin with, even to now understand how when a high-risk neuroblastoma is diagnosed, to predict that they will relapse versus those patients which do respond to existing therapy. We think there's really good potential in this technology to undertake that as a kind of diagnostic in those early treatment stages, to say this patient should be in a very high risk category versus say a high risk and will support existing protocols. But yeah, once we actually then can predict those patients which are at a high risk of relapse, we can also use the genetic features of those cells to then individualise treatment. And I think this is really going to be the solution long term for curing patients, that a one size fits all kind of approach isn't really going to be enough. Yeah. We're going to need to undertake what they call personalised medicine or precision medicine. So, and we think while some of these things are in place, and where some of the people working on the project are already undertaking a big precision medicine clinical trial, we think that this will be the kind of next step where we're not only just using the tumour as a whole, but we're able to look at those individual drug-resistant cells and then cater cocktails of drugs to target the whole tumour. Make sure we get rid of those hidden cells and the tumour relapse never occurs.
Okay. So the barcode is acting really as a unique identifier based on a sort of collection of genetics. You're understanding then that this cell's got certain genes within it, which then is going to be useful for you to build that knowledge of actually, if this cell survives everything that's thrown at it and it still survives, we need to target specific genes within that cell. Is that the natural conclusion?
Yeah, so the barcodes are, one of the strategies that we can use to really directly trace those cells before and after treatment. But in parallel, we get the genetic information that defines that cancer cell. So it may have a particular genetic feature which makes it vulnerable to drug X or drug Y, but we never know which drug to give or treat the tumour with, because that's so unique per patient. So really we can break that down, and on top of learn those drugs which work more effectively against those drugs, like the chemotherapy resistant cells. So we plan to screen a panel of drugs for which we will then try and reverse that resistance factor at a genetic level. Yeah.
So that would be massively exciting if you were able to do that, because obviously then it would make the treatment effective, and obviously with no relapse. So that would be really a huge breakthrough. So in terms of timing, what sort of is, everybody always wants obviously a cure tomorrow, we all do for all children. What, obviously research does take a lot of time getting all the data, so what's sort of the time frame on this project?
Look, to roll it out in terms of clinical care, I think we would be aiming in the next sort of 3 years or so to have that preliminary evidence that we can use some of these technologies as a risk prediction diagnostic. And we've got the clinical studies ongoing where we can actually roll that out in a prospective manner. But currently it's all retrospective, trying to match the genetic features to patients already undergoing treatment. So that would be, I guess, our plan at the end of this project. We're building that evidence to launch that prospective clinical trial for risk prediction. Longer term, maybe 5 years, we would, really hope that we can start using this information to predict new therapy in a personalised medicine context. So that's the goal, I think, in that time frame.
So stage 1 is the diagnostic, and then stage 2 is actually from all your screening and testing drugs is actually also being able to recommend certain drugs or treatments which will obviously improve the survival chance for that child.
Yeah, and within the project that has been funded by Neuroblastoma Australia, we'll be doing proof of concept type studies. So for instance, in laboratory-based models, we will test whether our predictions work more effectively. So that's definitely one thing which will be a stepping stone towards clinical translation. I would say also a huge benefit to the project, and something which we really think is important, is just the mechanistic resource that we will have to understand drug resistance, and that will really help the whole neuroblastoma field, I think, but potentially the technology can be applied to lots of different cancers as well, so we can start seeing how we can link that to different cancers, but our primary focus is neuroblastoma because the intrinsic nature of neuroblastoma cells and makes it very well suited to this, because drug resistance is complex and certainly something that needs new therapies. So there's definitely a kind of clinical need as well.
Yeah.
So yeah, I think we're really excited from multiple levels here, from discovery science right up to clinical potential and translation.
Yeah.
So that's the goal,
Yeah.
and sort of really been made possible by Neuroblastoma Australia, to try and undertake this kind of new stuff, which I think is hugely exciting for us as the investigators, and I think has a lot of potential. So.
Great, thank you. So just on that, I mean, and why do you think it is important for Neuroblastoma Australia to give out these grant funds? Does it make a difference to scientists like yourself?
I think it's huge, yeah. So this is a project where we've gone for competitive kind of national level funding, even some international stuff. And I feel like a lot of funding is for very established research, which is a bit of a problem in a field which needs innovation. You can't be established unless you've done those kind of new approaches. So I think there's really an important place for this sort of funding from philanthropics like Neuroblastoma Australia, who can and really get us off the ground with innovative type approaches. So as someone who's of the belief that it's going to be a very complex pathway to achieve cures. We have to recognise that it's not going to be simple. To undertake these first steps in that innovative realm is what excites me the most, and certainly would never be possible without Neuroblastoma Australia. So,
Great,
yeah.
Thank you. I mean, we believe that there are lots of really great ideas out there, and that we need to make it possible for those really great ideas to come into fruition, to have that opportunity, because certainly current treatments, as we know, they're horribly toxic, and obviously they don't work a lot of the time either. So we just need to do better for the children. So it's fantastic to have great minds like Dr. Carter's on board. So thank you very much, Dan, for your support, and really exciting to hear about your research.
My pleasure, and thanks very much for supporting the project. And we're hugely excited to get started on this and trying to make things better for neuroblastoma patients. So,
that's great.
Yeah.
Thank you.